Welcome back to another Daishinfinity video. In this video, we're going to talk about the limit formula, the derivative formula of sine of x. Now, this states that the derivative of sine is just equal to the cosine. So we're just going to use the limit definition or the differential quotient in order to solve this equation. The limit definition of a function f of x is given by f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now what we're going to do is take the limit for sine. So we'll just take sine of x and we'll prime it. So it's just the same thing as the limit as h approaches 0, and we just put the input as x plus h. So we'll just have sine of x plus h minus sine of x all over h. Now the second thing we are going to do is we're going to take in consideration what sine of x plus h actually is. Now we know from trigonometry that sine of a plus b is the same thing as sine of a times cosine of b plus cosine of a sine of b. So for sine of x plus h, it's the same thing as sine of x cosine of h plus cosine of x sine of h. So indeed we'll get the limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h all over minus sine of x and all over h. Now let's find common factors. So we have sine of x all over here and over here. So we just put this over here. So we're just going to split the fraction into two. H approaches 0 of sine of x, and then we'll have cosine of h minus 1 all over h plus cosine of x sine of h over h. Now the sum of the limits. So if I have a limit of a plus b is a limit of a plus the limit of b. Now the proof of this formula is going to be soon. Indeed, we're just going to take the limit of those individual ones. So we'll just have the limit as h approaches 0 of sine of x cosine of h minus 1 over h plus the limit as h approaches 0 of cosine of x sine of h over h. Now let's look at the sine of x and the cosine of x. The sine of x and the cosine of x has a variable x and doesn't include any variable that is h. So from looking at the perspective of the variable h, it's just a constant. So the limit of a constant is just a constant by itself. So we just put it outside the limit. So we can just say is the sine times the limit as h approaches 0 of cosine of h minus 1 over h plus the plus cosine of x times the limit as h approaches 0 of sine of h over h. Now let's talk about this and this. If we can solve the limits of those two, then we can have the formula for the derivative of the sine. So let's just first of all take this one, and then afterwards we'll take this one. So the first limit we're talking about is the limit as h approaches 0 of cosine of h minus 1 over h. Now how can we write cosine of h minus 1? We know from trigonometry that cosine of any number x and 1 minus cosine over 2 is just the same thing as sine squared of x over 2. So if we want cosine of h minus 1, we'll just multiply 2 on both sides, which will give us minus 1 minus cosine of x is the same thing as 2 times the sine squared of x over 2, and then we will just multiply everything by negative 1. So we'll have cosine of x minus 1 is equal to 2 minus 2 times sine squared x over 2. So we can take this and just transition the x to the h. So we'll have cosine of h minus 1 is equal to 2 minus 2 sine squared h over 2. So this is our definition for cosine of h minus 1, and we divide the whole thing by h. So the complete limit is just going to be equal to the limit as h approaches 0 of negative 2 sine squared h over 2 over h. Okay, now let's just take the limit of this expression. Now, if we take the limit as h approaches 0 for this expression, h over 2, when we plug in 0 into the h, then we'll have 0 over 2 equaling 0, so sine squared 0 over 0. But over 0, we cannot do this. So it's an indeterminate form, so we just have to do more work to it. Now we're going to do it by a squeeze theorem, stating that we are going to take some simple function. Let's take sine of x, for example. Sine of x looks like this for x bigger than 0. And let's take x, for example. And let's take the function 0, for example. So we have 0 and the function x and the other function sine of x. Now we can state that for small x, okay, for small x bigger than 0, we can state that sine of x is indeed bigger than 0 but smaller than x for x bigger than 0 until, let's say, pi. So the interval from 0 to pi, we can state that this inequality is true. So we are going to use h for the variable, and when we do it, we'll have 0 is smaller than sine of h is smaller than h. Now we have h over 2 in this limit, so we just say, okay, 0 is smaller than sine of h over 2 is smaller than h over 2. Now we can square both sides, all of them. So we have 0 is smaller than sine squared h over 2 is smaller than h squared over 4. And let's multiply 2 on all sides, so we just 0 times 2 is 0 is smaller than 2 times sine squared of h over 2. So we're just going to try to get the expression by itself, and it is smaller than h over 2 over 2. Now what we also have is minus sign in front of the 2, and we all divide by h, so we're just going to multiply everything by negative 1 first, which will lead us in 0 is smaller than negative 2, and because we are multiplying by a negative number, the sign of the inequality would change to the opposite side, so negative 2 sine squared h over 2 is bigger than negative h squared over 2. And the last thing we are going to do is divide everything by h, so 0 over h is 0 is bigger than negative 2 sine squared h over 2 over h, and this is even bigger than negative h over 2. Now we're going to at least take the limit as h approaches 0. Okay, so the limit as h approaches 0 of 0 is 0. So this is 0. And we're just going to write sine squared h over 2 over h is bigger than. Now the limit as h approaches 0 of minus h over 2 is 0 over 2, and 0 times 1, negative 1 is just 0. So here we also have 0. Now which number is between 0 and 0? So 0 is bigger than 0, negative 2 times sine squared h over 2 divided by h is bigger than 0. It's only true if this expression is equal to 0. So we can state that the limit as h approaches 0 of negative 2 sine squared h over 2 over h is indeed 0, which is also equal to the limit as h approaches 0 of cosine of h minus 1 over h. And since this was multiplied by, I think, sine, so the whole expression for the first Roman numeral is equal to 0. So we can state that 1 is equal to 0. Now we have the second Roman numeral stating that we have the cosine of x times the limit as h approaches 0 of sine of h divided by h. So we're going to take this limit by using another method. Now what is the limit of this expression? Now let's take the squeeze theorem again, and let's look at another graph. So sine of h looks like this, and we will take in consideration that h as a function is always bigger than, let's say, sine of x for h bigger than 0. Now if we take tangent of h actually looks like this. Let's take another color. So you go up like this, go down like this, and then repeat itself again and again. But we can see for small values of h that sine of x is always smaller than h. Sorry, sine of h is smaller than h, and h is smaller than tangent of h. Now we have the expression sine of h over h, so we'll all divide by h. And we still see that sine of h over h is smaller than 1, is smaller than tangent of h over h. Now what is tangent? Tangent is sine of h over cosine of x, cosine of h. So it's the same thing as sine of h over h is smaller than 1, is smaller than sine of h over cosine of h times h. So we're just going to multiply everything by cosine of h, which states that we'll have something like this. We'll have the sine of h over h times cosine of h, smaller than cosine of h, smaller than sine of h over h. Now look, before we dive right into this expression, we look at this expression, and we see we want bounds surrounding sine of h over h. So we have sine of h over h and the 1 over here. So we can still write the smaller than 1 over here. So 1 is the biggest value over here for any h bigger than 0 for small values of h over here. So we just can ignore this part and then just focus on this inequality, since this inequality can squeeze sine of h over h right now. Now let's use the limit definition as h approaches 0. Now let's put h into the cosine of h, so we just have 0 plus over here is smaller than sine of 0 plus, so 0 plus over 0 plus is smaller than 1, and the limit of 1 is just the 1, and the cosine of 0 plus is almost just equal to 1, so 1 is less than sine of h over h is smaller than 1. So we just have squeezed both of the sides, and we see that the number is both the same. So the limit as h approaches 0 of sine of h over h should be equal to 1. And since this is multiplied by cosine of x times 1 is thus cosine of x. So now we have proven that the derivative d dx of sine of x is equal to just cosine of x. I hope you like this video. It's a long video because of the limit definitions. So we had to use the squeeze theorem and not the L'Hopital's rule, because if we use the L'Hopital's rule, we would use the derivative of the function, which we're trying to prove right now. So we have to pretend we don't know the definition. Okay, now see you in the next Daishinfinity video. See ya.